Okay, so we have the square with corners A, D, B, and C, and it undergoes some form of deformation so that we now have A, D prime, B prime, and C prime. This new shape is drawn with the dashed lines. Distance from A to D prime is 53 millimeters. D prime to B prime is unknown but also unnecessary. The displacement from C to C prime is 8 millimeters, and the displacement from C to B prime is 3 millimeters. And we're asked to find the shear strain. The shear strain for the x and y axis for A and D prime and C prime and B prime. So normally the formula that you do that for is going to be equal to pi over 2 minus some angle, or it's going to be some angle minus pi over 2. At least that's how we're doing it in this video. That's going to depend if this angle is larger or smaller than 90 degrees or pi over 2, because for these problems we want to have all of our answers in radians. So right here we have the square. Each length originally was 50 millimeters, and so we knew that here at A we had this 90 degree angle. But now, as you can see, after the deformation, which is a change in size or shape, that the new angle between this x-axis, or A, and D prime is 91.5 degrees. This has been an increase in angle. So I'm just going to scroll right here. So gamma xy of A prime D prime is pi over 2 minus this larger angle, 91.5 degrees. To get this into radians, though, we're going to need to multiply our 91.5 times pi over 180, and that results in negative 0.0262 radians. Now, if this angle is 91.5, the square was 90, then we know what this angle was. Of course, it's 1.5 degrees. So if I want to get the height from the base of the square to this top where B prime is, we're going to need to use that angle. Using some basic trigonometry, we know that this angle right here is 1.5 degrees. So 53 times the sine of that angle will get us 1.39. Now 53 is the hypotenuse, 1.39 is this base, and so we can then deduce that this length is 52.98 millimeters. So I've redrawn this triangle right here. This is our original C. This is our, this is not our original C. Our original C would actually be somewhere like right here, because this is 3 millimeters and this was the 8 millimeters from C to this is C prime and this is B prime. Okay, but C was only horizontally displaced, so that's why we just drew this line directly down from B prime to the platform. Okay, or platform x-axis. Okay, so I wrote this two angles right here, and I want to ask which one are we going to be solving for, alpha or beta? Beta, which one do we need to find the gamma xy for the CB prime? So we're actually going to be using this beta right here, which means we're going to need to solve it using the law of cosines, which is c squared equals a squared plus b squared minus 2ab cosine c, right? So of course, to do that, we need this length. We need to be able to find this length, which is just the square root of 52.98 squared plus 11 squared, or 54.11 millimeters. So I've gone ahead and written out the law of cosine so that we could find the cosine of C. C is your desired angle, or cosine of C for your desired angle, and the side opposite to that is the C squared. So we have 52.98 squared minus A squared minus B squared all over negative 2AB. And that results in an angle of 78.27 degrees. But again, we want to use radians, so we can go ahead and write this as 78.27 pi over 180. So if you remember, for when we were doing A prime D prime, which was the first and relatively easier calculation, we did pi over 2 minus the larger angle, but this time we've had a decrease in angle, so we're going to do 78.27 pi over 180 minus pi over 2. And that'll give us our gamma xy, our shear strain, as negative 0.205 radians. So that would be the two shear stresses that we were asked for. There's one more thing that maybe is worth looking at, and that's the normal strain developed along the line from D to C when we get D prime to C prime. So finding that's easy. It's just our new length minus the original length divided by the original length. And again, to solve this, we just need to use Pythagorean for the original length, and then we can use our law of cosines to find the new length. So I'm not going to spend much time. In fact, I'll just show on the screen right here how I found that new length. And I wrote maybe help right here because originally as I was solving the required questions, I was playing around just trying to figure out what maybe I could do. So that is the end of the video. I hope this has helped solve a little bit of the shear strain questions or problems we may have.